Metal manufacturing and machining combine heat, precision, and power, transforming raw steel into essential parts that drive industries and shape the modern world. A powerful hydraulic excavator is used to recycle an old bus efficiently. With its strong mechanical arm and sharp claw, the machine grabs, crushes, and cuts the bus into smaller fragments. It applies immense pressure to dismantle the metal frame, body panels, and engine components. As the bus is torn apart, the excavator also assists in separating metal parts from non-metal materials like plastic, rubber, and glass. This careful separation is crucial for recycling, as metallic pieces can be collected, melted, and reused, while the remaining non-metal materials are sorted and processed for further treatment or disposal. The production of aluminum alloy steel cable heads starts with premium raw materials supplied by internationally recognized smelting manufacturers, ensuring outstanding quality and consistency. The company operates a 6,000-ton large seamless extrusion press, capable of producing seamless cable heads up to 110 millimeters in diameter. This advanced equipment allows high precision and durability in every product. The manufacturing process consists of several essential stages. First, the raw materials are cut accurately using a computerized automatic sawing machine, which guarantees consistent dimensions for each billet. Next, both the raw materials and the mold are preheated to the required temperature to enhance metal flow and prevent internal defects. During the extrusion stage, the preheated aluminum billet is pressed through the mold to form a dense and seamless cable head. After extrusion, the semi-finished cable head is cooled, trimmed, and checked for dimensional accuracy. To ensure high performance, the factory performs regular sampling and mechanical testing throughout the production line. Every finished cable head undergoes a tensile strength test to confirm its load-bearing capacity and structural integrity. Through strict quality control, advanced extrusion technology, and continuous improvement, the company delivers durable, precise, and reliable aluminum alloy steel cable heads that meet international standards for safety and performance. The double jointing process is a key operation in the production of long pipeline sections, designed to improve handling efficiency and reduce field welding time. This process joins two standard 40-foot pipes into a single 80-foot double joint. It begins when standard length pipes are loaded onto the double joint rack, where ropes provide cushioning as the pipes move through the system, preventing damage to the pipe surfaces. Each incoming pipe is supplied with standard stick rod bevels, which must be accurately machined into submerged arc welding bevels to ensure a proper joint configuration. The pipe is first rolled into the end-facing station, where the pipe-facing machine is inserted into one end. This machine precisely machines the bevel to exact specifications. After the bevel is completed, it is carefully checked for accuracy before the pipe is released. The pipe is then moved to the preheating station, where it is heated to over 100 degrees Celsius to remove all traces of surface moisture and prepare it for welding. At the outside diameter 1 welding station, 2 pipes are rolled into position. A spacer ensures the correct alignment of the pipe ends, while an internal clamp is inserted to hold them securely in place during welding. The weld head is then lowered onto the pipe, and the submerged arc welding process begins. In this technique, the arc burns beneath a blanket of granular flux that protects the molten weld pool from oxygen and contaminants. A vacuum recovery system collects and recycles the unused flux for future use. The welder keeps the arc centered within the bevel by steering the weld head's pointer. Once the first weld pass is complete and the tie-in made, the weld head and internal clamp are withdrawn, and the pipe is rolled out. Next, at the outside diameter 2 station, the cap pass is applied. This second weld pass strengthens the joint and requires no further grinding or cleaning. The pipe then moves to the internal diameter welding station. Here, the internal welder, mounted on a movable boom, travels to the center of the pipe. Using a laser guidance system, the welder performs the internal weld pass, ensuring perfect penetration and alignment. After welding, a cleanup worker enters the pipe on a cart to remove any flux and slag residues. Finally, the welded joint undergoes X-ray inspection. One technician places an X-ray tube inside the pipe, while another positions unexposed film over the weld area. The X-ray is taken, and the film is developed and examined within minutes to verify weld quality and integrity. The completed double joints are then lined up on the rack, where loaders transport them to the yard, ready for shipment to the pipeline right-of-way for installation. A 300 horsepower DC motor was brought into a professional motor repair facility after it was found to have a grounded field coil. This serious electrical fault required a complete dismantling and evaluation to determine the extent of damage and decide on the appropriate restoration process. The inspection results confirmed that the motor needed to be rewound and fully overhauled to restore its electrical and mechanical reliability. The overhaul process began with complete disassembly of the motor. The technicians carefully removed the end housings, rotor, field coils, and other internal components. Each part was inspected for wear, corrosion, and insulation failure. The entire motor frame and internal parts underwent deep cleaning using industrial degreasers and high-pressure air jets to eliminate dirt, oil, and carbon deposits accumulated during operation. Cleanliness is essential to prevent future insulation breakdowns and to ensure efficient cooling of the motor during service. Once cleaning was completed, attention was turned to the field coil rewinding process. The damaged and grounded field coils were completely stripped out. The coil slots were then carefully cleaned, insulated with high-temperature resistant materials, and rewound using high-grade copper wire that matched the original winding specifications. After winding, the coils were impregnated with varnish and baked in a curing oven to enhance insulation strength, moisture resistance, and mechanical rigidity. Meanwhile, the armature and commutator were examined. The commutator surface was machined smooth, and its mica insulation segments were undercut to improve brush contact and reduce arcing during operation. The armature was dynamically balanced to eliminate vibration and ensure stable rotation at full load. The drive end housing was then re-sleeved to correct worn bearing fits, restoring precise alignment of the rotor shaft. Both drive end and non-drive end bearings were replaced with new, high-quality bearings to guarantee smooth, quiet performance. Lubrication channels and seals were checked and renewed to prevent future leakage. After reassembly, the motor was subjected to electrical and mechanical tests. These included insulation resistance, high potential testing, no load run, and vibration analysis. The final dynamic balancing ensured that the motor ran smoothly, with minimal noise and current fluctuation. Upon completion of the overhaul and rewind, the 300 HPDC motor was restored to near-new condition. With renewed insulation, precise mechanical alignment, and upgraded components, it was ready to deliver efficient, stable, and long-lasting performance in demanding industrial environments. The strip cladding system is an automatic surface welding process used for pressure vessel components such as pipes and tube sheets. It employs two main techniques: submerged arc welding and electro slag cladding. In submerged arc welding, a strip electrode is continuously fed under a layer of flux, where the arc melts the strip and base metal to form a corrosion-resistant layer. In electro slag cladding, the strip is melted by the heat of molten slag instead of an arc, allowing for thicker deposits and higher efficiency. Both methods ensure strong bonding, uniform coating thickness, and excellent metallurgical quality, providing durable protection for the pressure vessel's inner surfaces against corrosion and high-temperature conditions. The Turbine Hydropress Plant carries out a full production cycle using its own extensive equipment base. The process begins in the welding and preparation workshop, where metal sheets up to 6 meters long are precisely cut. Skilled specialists perform various types of welding with seam thicknesses up to 400 millimeters, ensuring high structural strength and quality. In the forging and pressing shop, powerful hammers and 2,000-ton hydraulic presses shape billets into shafts, discs, rolled rings, and other forged products according to client drawings. The iron casting shop operates a massive furnace capable of producing castings weighing up to 18 tons with wall thicknesses not less than 20 millimeters. Modern materials and improved techniques are applied to enhance the quality of cast iron parts. All blanks from these departments are then transferred to machining workshops. The plant is equipped with unique machines capable of planing parts up to 18 meters long and 4 meters high, grinding surfaces up to 14 meters long and 3.5 meters wide, and turning pieces up to 2.5 meters in diameter and 12.5 meters in length. Overhead cranes with a lifting capacity of 100 tons handle large components safely. In 2017, a new heat treatment shop was launched, providing normalization, quenching, tempering, nitriding, and carburizing. Continuous modernization and new high-precision equipment strengthen production, while the assembly shop, the heart of the plant, brings together all components into finished heavy-duty machinery. The daily work of a mechanical plant, specializing in the machining of metal components. Inside the workshop, various CNC lathes, milling machines, and drilling centers are seen operating simultaneously, shaping raw metal into precise industrial parts. Skilled machinists monitor each process carefully, setting up tools, adjusting cutting parameters, and ensuring dimensional accuracy. The factory handles a wide range of metals such as steel, aluminum, and cast iron, meeting the demands of both small and large-scale production. Parts of different sizes and complexities are being machined, from simple shafts and flanges to intricate housings and gear components. The production process follows strict technical drawings and tolerance standards, with regular inspections performed using measuring instruments. The plant's workflow demonstrates the perfect balance between human expertise and advanced technology. Modern equipment provides high productivity, while the workers' experience guarantees quality and reliability. Overall, it reflects the professionalism, precision, and dedication that define the mechanical machining of metal parts in the factory's everyday operations. Behrens Maschinenfabriken BV specializes in the precise production of high-quality gearboxes and gears. The process begins when raw steel pieces arrive at the factory and are turned into pre-machined blanks. These are then milled to create the initial gear shape. Afterward, the components undergo heat treatment to increase hardness and strength. The final gear teeth are finish milled with exceptional precision, reaching tolerances of up to 2 microns. Using advanced 5-axis CNC gear milling and proprietary mathematical models, Behrens achieves optimal tooth geometry for maximum efficiency and durability. The company also designs custom gear profiles, such as the stronger S-tooth, to meet specific requirements in industries like maritime, mining, and power transmission. Barney Guida is a company specialized in high-precision mechanical manufacturing, combining advanced technology with skilled craftsmanship. The production process begins with the careful selection of high-quality raw materials, which are then machined using modern CNC equipment. Each component is produced with extreme accuracy to meet strict dimensional tolerances. The company focuses on the complete production cycle, including turning, milling, grinding, and surface finishing. Automation and robotics are integrated into many stages to ensure consistency and efficiency. However, every detail is also verified by experienced technicians through rigorous quality control procedures. Barney Guida continuously invests in innovation, digitalization, and sustainability to improve productivity while maintaining environmental responsibility. Thanks to this combination of technology, expertise, and precision, Barney Guida delivers reliable mechanical components used in various industrial sectors. The major overhaul of the steam turbine at Tampieri Energy by Depreto Industry involved a complete inspection and restoration process to ensure reliable performance and prevent unexpected shutdowns. First, the turbine unit was shut down and carefully disassembled on site. The rotor, being the heart of the machine, was removed and transported to the workshop for detailed inspection. After micro-sandblasting, non-destructive tests were performed to detect cracks or defects. If any damage was found, the rotor was repaired or modified according to the client's needs. Subsequently, dynamic balancing was carried out to restore smooth operation. At the same time, engineers and technicians worked on other turbine components, such as bearings, seals, and casings. The static sealing system was upgraded with floating rings, which improved performance consistency and reduced clearance losses. After all parts were inspected and reassembled, alignment and final testing were performed to verify efficiency and safety. This comprehensive overhaul restored the turbine's original output from 2012 and improved its technical reliability for continuous operation in the vegetable oil production plant. Founded in 1932 as a company for material handling technology, Zash Handling has been developing, producing, and supplying manual handling equipment worldwide for more than 25 years. Each device is individually customized to meet specific customer requirements, focusing on optimizing workflow, improving ergonomics, and reducing physical strain on workers. The company's intelligent handling solutions help minimize workplace-related musculoskeletal disorders and enhance employee well-being. As a full system provider, Zash Handling offers a complete range of solutions, from simple mechanical lifting tools to highly complex systems, all based on a standardized modular design. With international sales experts and a fully equipped showroom for real product testing, the company ensures practical and customer-oriented solutions. Continuous product development, lightweight designs using carbon components, and comprehensive after-sales services demonstrate Zash Handling's commitment to innovation and quality. After the steel billet is heated to the proper forging temperature in the furnace, it is discharged through a chute and placed beneath the large forging hammer. At this stage, the metal is glowing red and in a highly plastic state, allowing it to be shaped effectively under the repeated impacts of the hammer. The hammerhead descends with tremendous force, striking the billet again and again. Each blow plastically deforms the hot steel, causing it to spread laterally and elongate according to the blacksmith's manipulation. During this free forging operation, the billet's internal grain structure is refined, its density is increased, and its mechanical strength is significantly improved. The operator carefully rotates and repositions the billet after each series of strikes to ensure even deformation and maintain symmetry. This manual control helps produce a well-distributed shape, suitable for the following precision processes. Once the billet has been forged to the correct proportions, the next step is hole punching, which transforms the solid billet into a ring-shaped preform. While the billet remains at the forging temperature, it is positioned on the anvil, and a hardened steel punch is aligned precisely with its center. The alignment is crucial because any misalignment can cause cracks or uneven walls. Using controlled, repeated blows from the forging hammer, the punch is driven axially through the billet. With every impact, the metal surrounding the punch flows outward, forming a circular opening. The process must be carried out swiftly to prevent excessive cooling, which could reduce the billet's plasticity. When the punch finally breaks through the bottom, the billet has a clean, centered hole, that defines the internal diameter of the future ring. This operation is fundamental because it establishes the basic geometry for the next stage ring rolling and ensures the metal flow remains uniform during expansion. The pierced billet is then transferred to the ring rolling machine while it is still hot. In this stage, the billet is placed between the main roll and the mandrel. As the main roll rotates, it exerts strong pressure against the billet's outer surface, while the mandrel supports the inner surface. The combination of rolling pressure and rotation causes the wall thickness to gradually decrease while the outer diameter expands. Through continuous rolling, the billet transforms into a seamless ring. The process requires precise control of rotation speed, roll gap, and temperature to avoid defects such as cracks, eccentricity, or uneven thickness. Continuous monitoring ensures that the metal's grain flow follows the circular contour of the ring, giving the final product excellent structural integrity, fatigue resistance, and toughness. After ring rolling, the ring undergoes the final shaping operation known as axial closed die rolling. In this stage, the preformed ring is inserted into a die system consisting of a stationary lower die and a rotating inclined upper die. As the upper die rotates, it gradually moves downward, closing the gap between the dies and applying a uniform compressive force. The metal flows into the cavity, and the ring is shaped precisely to its final form with accurate dimensions and smooth surfaces. This method ensures tight tolerances and excellent surface finish without machining defects. Throughout the entire forging sequence, from furnace heating, free forging, and hole punching to ring rolling and closed die finishing, temperature, deformation rate, and alignment are carefully monitored. Each stage contributes to improving the microstructure, achieving consistent mechanical properties, and ensuring dimensional precision. The process of rolling a large diameter, thick-walled metal cone begins with the preparation of a pre-cut steel plate. The plate is first cleaned and positioned on the working table of the rolling machine. Its edges are aligned carefully to ensure proper geometry before forming begins. Next, the plate is fed between the upper and lower rollers of a powerful 3-roll or 4-roll bending machine. The operator adjusts the roller pressure and positioning according to the required cone shape. During rolling, the lower rolls rotate to pull the plate forward, while the upper roll moves vertically to apply forming pressure. At the same time, the lateral rolls are adjusted at an angle to gradually create the taper needed for the conical profile. This process is repeated several times, with continuous repositioning and incremental bending to ensure a uniform wall thickness and precise conicity. As the cone takes shape, the operator checks the curvature using templates or measuring tools. Corrections are made by fine-tuning the roller settings. Once the desired cone geometry is achieved, the rolled edges are brought together and tacked for welding. The cone is then removed from the machine for final inspection, trimming, and full circumferential welding. This controlled rolling process ensures high dimensional accuracy, smooth surface quality, and excellent structural integrity of the thick-walled cone.